Hello friends, I welcome you in lecture number 21 on relations. In this lecture we are going to discuss one example on composition of relations. We have discussed how to find out composition of two relations in lecture number 20. So if you are not seen lecture number 20, then I suggest you to watch that lecture first and then go for this lecture. In lecture number 20 we have discussed when we can define composite of relations and what is the meaning or definition of composition of relations. So with that definition of composite relation in our mind, we try to find out composition of given relations in this example. Here we are having two relations denoted by capital R and S on a set of positive integers, which is denoted by this notation capital I. Here I is the notation for the set of positive integers, and we know that set of positive integers is nothing but set of natural numbers. So sometimes they can use this notation or this notation for the set of positive integers. So this R and S are defined in this way. In R we have ordered pairs of the form x, 2x, where x is any positive integer. For example, if I take x equal to 1, then I will have 1, 2 in this relation R. Similarly, if I take x equal to 2, I will have 2, 4. If I take x equal to 3, I will have 3, 6. So this second component is multiplied by second component is even multiple of first component. We can see here I have x and here 2 times x, that is even multiple of this x. We are multiplying by 2. Similarly, relation S is defined in this way: x, 7x, where x is any positive integer. So for different values of x we will have different ordered pairs. Here for x equal to 1 I have 1, 7. For x equal to 2 I have 2, 14, and so on. So there are infinite number of ordered pairs in both the relations R and S, because here x is from the set of positive integers, and we know that set of positive integers is infinite set. So for different values of x we will have different ordered pairs in both the relations. And here we are asked to find out composition of R and S, composition of R with itself, composition of R with itself or 3 times, that is R3, and here composition of R, S and R. So we will find out all these required compositions one by one. Before that, we recall the definition of composition. Suppose we have two relations R and S, then composition of R and S is the set of all those ordered pairs of the form x, z such that there exists some y such that ordered pair x, y is in relation R and ordered pair y, z is in relation S. If xy belongs to R and yz belongs to S, then ordered pair xz is in the composition of R and S or in composite relation ROS. So this is the definition of R composite S. So here we have to decide that R composite S is having which ordered pairs, or what will be the nature of ordered pairs in R composite S. For example, here this relation has infinite number of ordered pairs, but we can write all those ordered pairs in this form x, 2x, that is R contains this type of ordered pairs in which second component is multiplied by 2 with first component. Similarly, S contains all those ordered pairs in which second component is multiplied by 7 with first component. So here also I have to decide that what is the nature of elements of R composite S. So by definition we have ordered pair XZ such that there exists some Y such that X comma Y is in R and Y comma Z is in S. So if I consider any ordered pair XZ in R composite S, suppose I have XZ in R composite X, then we must have some positive integer Y such that ordered pair XY is in relation R and ordered pair YZ is in relation X. Here I am interested in the nature of this ordered pair XZ. So I am going by definition. Suppose there is some element XZ in the relation R composite S, then by the definition of composite relation we must have some positive integer Y such that ordered pair XY is in R and ordered pair YZ is in S. Now ordered pair XY is in R implies if ordered pair XY is in R, then we know the nature of elements in relation R. Here second component is multiplied by 2 with the first component. So if ordered pair XY is an element of R, then Y must be equal to 2x. So from this I can write that Y is equal to 2x. Similarly, ordered pair YZ is in relation S, and in relation S we have this type of ordered pairs in which second component is multiplied by 7 with the first component. So YZ belongs to S, therefore this component Z is multiple or is multiplied by 7 with the first component. And we are interested in the nature of elements of R composite S. So now we have this Y equal to 2x and Z equal to 7y. So we can put value of Y in this Z equal to 7y. Y is 2x here, so I put Y equal to 2x and I find that Z equal to 14 times x. So if I have ordered pair XZ in R composite S, then I must have Z equal to 14x. So I have obtained the nature of elements in R composite S. So I can write that R composite S is nothing but ordered pair x comma 14x, where x is in the set of positive integers. So whenever we have infinite number of elements in a given relation, then we should write our relation in this form. We should write some particular form which will give us any element in the given relation. So now we have obtained that R composite S is the relation having this type of elements, order pair x comma 14x, where x is any positive integer. Now in the similar way we find out R composite R. So nature of elements of R is order pair x comma 2x. So now we try to find out R composite R. So for that we start by taking arbitrary element in R composite R. Let xz be any element in R composite R. Then by the definition there exists some positive integer y such that ordered pair xy is in R, that is here first relation is R and second relation is also R. So yz belongs to R. Now nature of elements of R is that order pair x comma 2x, that is this component is multiplied by 2 with the first component. So because xy is in R, we must have y equal to 2x, and because yz is also in R, we must have z equal to 2 times y. And here I can substitute value of y. Y is 2x, that I substitute here, and I find that z equal to 4 times x. So we have obtained the nature of elements in R composite R. If xz is any element of R composite R, then we must have z equal to 4x, where x is any positive integer. Therefore R composite R is equal to ordered pair x comma 4x, where x is any positive integer. So in this way we can decide easily composition of given relation. Here I have to obtain R composite R. So for that, if you have seen lecture number 20, then we know that composition of relation satisfies associative property. So if I take R composite R in a group, and if I take composition with R, or I can write in this way also, these two are always equal because associative property is satisfied by this operation, composition of relations. So we write this in this way, R composite R and R. So we have to find out composition of R composite R with relation R, and here by definition we have this type of elements x, z in this relation such that there exists some y in capital I such that ordered pair x, y must be in first relation, that is ordered pair x, y belongs to R composite R, and ordered pair y, z belongs to second relation, that is R. Here we consider composition of this relation R composite R with R. So we have this type of elements in this relation. Now from this we can say that because xy is in R composite R, and we have obtained the nature of elements of R composite R. Here I have to multiply second element. I have to multiply first element by 4 to obtain second element. So if I consider xy belongs to R composite R, then I must have y equal to 4x. So because this is in R composite R, y is equal to 4x. Similarly, ordered pair yz is in R, and what is the condition for element to be in R? In relation R, we have x comma 2x, that is this component is obtained by multiplying first component by 2. So if yz belongs to R, then we must have z, which is second component, is multiplied by first component, which is y here, and y is 4x, so that we substitute here. So I have 2 times 4x, and that is going to be 8x. Therefore this R composite R is equal to ordered pair x comma 8x, where x is any positive integer. So in this way we can easily decide this type of compositions, and this I leave for your homework. You can find out this R composite S composite R, and you can give your answer in the comments. This we can rewrite as R composite S composite R. So we have already obtained R composite S, and you have to take composition of R composite S with relation R, and you should give your answer in the comment section. and we can verify. So this is all about this session. Thanks for